start this recording. All right. So, did you guys see the final exam schedules posted? So we have a final exam, and it is, I'm pretty sure that's the first day of exams on December 8th. First time slot possible. I'm pretty sure. I feel like it's the first day of exams at 9 a.m. So our final exam is on December 8th. I guess from 9 to 12. So if you haven't seen the final exam schedule, you can just Google Okanagan College final exam schedule, and it should come up with, I don't know, some scheduling webpage, and that's where you can grab them all. I think they might have separated the in-person classes from the online classes. So of course our exam is online and feels like a ways away still. It is. But now that you have the final exam schedule, now you can do things like book flights, and usually that's more important when we're in person, right? Everyone wants to go home, and you don't want to wait too long to book your ticket. And anyways, so the final exam schedule is posted and you can check it out. Okay, so I'll be honest, I've had a tough time this weekend because I keep going back and forth. So I know even I'm having a hard time justifying why you need to do this material besides becoming stronger in math, which is something that especially the data science guys really, really want. And so it will be, beneficial. But in terms of the course being called Applied Statistics, I'm really having a tough time kind of selling it to you guys. And so, and I can't decide what to do. There's very little that I can do, unfortunately, because, they told me to teach this stuff, and sure, okay, I do what I'm told. We all do, right? And then, oh yeah, assignment 2. Well, you can always get in touch with me and if there's something that you're working on and we can work through it together, or like I'm happy to do that, because I get it. These problems are so weird and not what you would be expecting out of an applied statistics course. So I feel really bad about that. And I'm still kind of, I don't know what our options are. I think we just have to keep going with this. I don't know how to make it more applied. I'm going to try. So we'll try to figure it out and kind of meet in the middle. I was looking at a completely different textbook. It's a free textbook, but you can check out, and it would be a completely different thing. It's called ISLR. I think it's an introduction to statistical learning. Maybe I shouldn't say Google, because then someone reading these might feel weird, but check out I'll change the color here. And it is by Tib Sharani, who's kind of a big name. Among others, but so I don't know what we can do about incorporating more of this into the course, but I'm going to try to weave some of this textbook. So this is a free to download textbook. Okay, and so I will try to incorporate some of this text into this course, okay? Because this one, this textbook, the Introduction to Statistical Learning, that one is really applied, and I think you might enjoy it a little bit more. And so, like I said, I'm having a really hard time kind of selling this textbook that we're working through right now to you guys. It's really long, it's really boring, but it is good material. So I'm not saying that it's not useful. It's definitely useful to have a strong mathematical background. But I know going into this course that it is probably weird. So I guess what I'm trying to say is I'm sorry, and I'm going to try to make it as good as possible. So I'll try to incorporate some of the ISLR textbook into the course. Really making me work for it. As if this material wasn't weird enough, or kind of, it's been a long time since I did this stuff. But what I want to do is I want to start chapter 2. Yeah. And so let's start chapter 2. And of course, it's going to be more theory. And I'm just going to see what I can do, try my best to make this still a fun course. I like to deliver fun courses, but so far this one is just not that fun. There, I'm on the record saying it. The ISLR might be, but it's an open textbook, and that's why I like it so much. And they have like lab problems that we can work through. It's, I think it might be a Springer text. Let me check. Oh, I don't have the, it just might be, but you should be able to, yeah, I think that's the one. But you should be able to get the free download. Just the PDF version. I think they make you pay for the hard copy one. What also, if any, let's see here. Is this the one? Sorry, it's still downloading. I had a test this morning and everyone was having internet connection troubles, and now I'm having the same. I guess it's a pretty big textbook. I'll check out that link after. Let's see if I can get back to you guys there. Oh yeah, so yeah, I mean, I'm gonna try to highlight any real world application that I can find. A lot of this is, you know, theoretical, and I'm gonna try my best to find real world questions that we can answer. And I think you're sending me direct messages, but maybe send them to everyone. It's okay. I addressed it, but Oh, a Brazilian university. Hey, that's fun. But also, let's see here. I think if I just search ISLR book. Yeah, it looks like the hard copy is published by Springer, but if you just go to statlearning.com, you can download the second edition. Nice. So it's just kind of fun because, I mean, they're not doing a ton of what we're doing in this class, but they are doing really applied stuff. So kind of two worlds collide. But I do remember you guys saying not so much applied. R is too hard, probably. Guessing. But this would give you some background too. Okay, so just check it out and see. And like I said, I'm going to try to incorporate some of this text into the course. And because it's free, that's a good thing, right? It's always there. And yeah. Okay. Yeah, all the R lovers are here. Exactly. Okay. Let's see here. Oh yeah. I had a big note that I had to highlight when the final exam is, so that I've done that. So now I think, and just kind of apologize with the material, I guess. I don't know. But we're going to do our best. That goes for all of us. And let's start chapter 2. Okay, so chapter 2 is on multivariate distributions. Oh, before I start chapter 2, from last Friday, I posted an MGF video in R. There's no exercises or anything. Just try to work through those. And I gave you the code chunks already. So just kind of be aware that that exists, but I'm not getting you to do anything. Oh, and I'll finish marking those assignments. Sorry, they kind of got pushed back. And then anyways, here we are. So I'm working through your assignments and I'm marking those, and I'll upload a new PDF where I've written kind of comments on it. Okay, so those will be up later today. Okay, that was all the things I wanted to say. So in assignment 2, I've got 2 questions, both involving R, both involving the second assignment, and I feel like they came in at the same time, so that's really funny. And so for the second assignment, definitely you can solve the first one in R. You could try to solve it all in R. That seems ambitious to me. For me, it's sometimes easier to just do it on pen and paper, but you're welcome to try. And then the first question, the question itself says use R, but you can use Desmos as well. So if you don't have Desmos already, Desmos is really useful. Oh boy, we've got coders amongst us. Feels like an interesting coding problem. Oof. Well, I wish you luck. I think you can do it. I haven't tried it. That's why I'm not 100% sure, but I encourage you to try it. So let's see here. So remember, Desmos is that free graphing calculator app, right? But it can even do crazy integrals like this. Right, and so this is one of the integrals that we're going to lead up to, or a double integral. So we're leading up to this in this section because we're going to have two variables now. We're going to have an x variable and a y variable, and they're going to change kind of together. Okay. Oh, haven't learned R before. That's okay. Well, that's even more reason for us to kind of slow it down on the R front. Okay, thank you for telling me. And so this is just kind of, I'm curious if anyone has bought this Hogg textbook. Don't worry if you haven't, because I posted chapter 1 for that reason. But I just want to know how bad I should feel if I change things up completely. If anyone, that is really good. That's what I want to hear. I hope, yeah. You guys have the PDF? Were you able to get it for free? I won't tell. I'll be happy if you did. Good. Okay. That's good. I just want to, yeah, so, okay. That makes me feel good. I'm happy about that. I guess I shouldn't say that in the recording. Nobody's listening. No, I'm happy about that. Good. So yeah, so because I don't want to say, oh, go buy the textbook, and then someone buys it, and then I change my mind and we go a different, anyways, I'm just trying to figure this course out. No one gave me anything to do. Anyways, it's enough about me. I'm really glad to hear that, and thank you for telling me. Okay, but for now, let's just keep going with chapter 2, and then we'll see what I can pull off here. Okay, so for that question about assignment 2, question 1, you can solve it using Desmos instead of R. In fact, it's a lot easier using Desmos. Okay, let's see here. Chapter 2 is on multivariate distributions. Okay. And we're going to start with section 2.1, which is the distribution of 2 random variables. So now we're moving from just one random variable x. How does it behave? How do we find probabilities associated with one random variable x? And now we're moving to, okay, now I want to keep track of 2 random variables. How do they change together? Okay. And so we're going to be talking about distributions of 2 random variables. Okay. And so we introduced a random variable x, which is a function that assigns some number to each outcome, right? So if heads is 0, tails is 1, for example, that's the most basic example, right? And so we introduced a random variable, capital X, as a function, x of some c, a lowercase c, which assigned which assigned a real number to each outcome C, in the sample space, which we denote by kind of a fancy capital C. So now we're going to introduce, we're going to define multiple functions, random variables. Okay, so we now define multiple such functions and introduce how to deal with what? Multiple random variables at the same time. How to deal with multiple random variables, RVs, I'll say, at the same time. Okay. So from here, we're going to start talking about random vectors. Now, we might have, n random variables up to xn, but they would all be arranged in kind of a vector form. So we introduced the idea of random vectors. Oops, that was weird. Random vectors there. Random colon vectors, no, random vectors colon. We can think of several random variables, several RVs, such as x1, x2, all the way up to x subscript n, as making up the elements of a random vector. As making up the elements of a random vector. And I'm going to make it kind of small here, but x just to fit it on the same page. So a vector, usually we close it off just like a matrix with square brackets. So we have x1, x2, all the way down to xn. There are going to be combinations of x1, x2, all the way up to xn that make up some event. And so we can define an event x, which is in A. Okay, we'll obviously do more examples once we introduce the discrete case and the continuous cases. And so for now, we're just introducing the general idea. So don't worry about it too much for now, but we'll get it on the page so we can define, get it on the plate. You have 1 minute remaining. No, we can define an event x in A corresponding to the random vector x lying in some region of A that's contained in Rn, right? And so that's the n-dimensional real value plane, right? Or it's not a plane anymore. Random variable x lying in some region A, which is in the Rn field. And we use the probability function to define the probability of this event. Again, not really going to make sense until we see what we mean here, but we're going to have it here anyways. So when we use the probability function to define the probability that X is in A of this event. We're going to build this by just considering n equals 2, right? So x1 and x2. So just two random variables. How do they change together? And then it'll extend to n random variables. But if we have a good handle on how two change together, then we can handle more. Okay. So we will focus on n equals 2 initially, and define the joint cumulative distribution. So now, because we have two random variables, they're going to have a joint cumulative distribution function, as opposed to X had a CDF. The CDF is what? It gives us the probability up to and including some point, right? And so we can do the same thing, but now we're going to have X and Y happening at the same time. Okay? And so, or X1 and or X2, the notation doesn't really matter. We use X1 or X2, Y1 or Y2. X and Y is probably the easiest to keep track of, at least. So define the joint cumulative distribution function of two random variables, X1 and X2, as, so the CDF, we always denote it with a capital F, X1 comma X2. This is what makes it the joint CDF. And the input is X1, X2. How we're going to read that is, well, that's going to be the probability. So remember back in the one variable case, one random variable case, we had fx of x was the probability that x was less than or equal to this input x. Same thing's going to go here, except now we're talking about x1 and x2. And so it's going to be the probability that x1 is less than or equal to lowercase x1, and x2 is less than or equal to lowercase x2. Okay. Versus for one random variable x, fx of x was the probability that x was less than or equal to x, right? So now we've just extended it to the two random variable case, and they have to be happening together, right? And so that's why you have this and here, or the intersection between these two events, right? Just like before, when we had, okay, so if I know the CDF of X, then I can use it to find different probabilities. We've seen that in Stat 230, for example, where we use, well, at the most basic level where we use the Z table, right? The Z table is continuously just giving, well, not continuously, but it's giving us the area to the left of each of these points, right? And so then we can use that, the areas to the left, which is the CDF, right? We can use that to find other probabilities. What's the probability of being between a Z of negative 1.24 and a Z of 3.19? So the Z table in theory is continuous, but the table itself, it has breaking points, right? It only goes to 2 decimal places. But if you use R or some other online calculator, it is continuous, but the Z table itself is not continuous. Although you could have a more precise table. Yeah, so it is continuous, yes. But yeah, what I got caught on was it only goes to 2 decimal places, right? But yeah, so as we have seen in the one random variable case, oh, yeah. But all variables being quantized. It depends on the random variable. So we have the discrete random variable, and then, oh, yeah. So, okay, I think I understand. Yeah, the accuracy. So the Z table, it is continuous, but what we're looking at is not continuous. Right. But it is continuous. I know. Good. So as we've seen in the one random variable case, we can use the CDF to calculate the probability of an event. Right, and so think back to the Z table, right, which gives the area to the left of Z's between negative 3.49 and 3.49. It goes further, but the table stops there, which gives, oops. The area to the left of Z scores between negative 3.49 and 3.49, which we can use to find any probability. Which we can use to find any probability. Right, probability, for example, the probability that Z is between negative 1.29 and 3.02. I don't know, I'm just making up numbers, right? That's going to be the probability that Z is less than 3.02 minus the probability that Z is less than negative 1.29, right? Thinking back to Stat 230. Right, and so this is the CDF up to that point, and this is a CDF. So we can use the CDF to calculate the probability of an event, right? And so here in this case, the event might be that the Z is between -1.29 and 3.02. So then we can break it up and we can talk about the different CDFs. Now we can do this for joint CDFs as well. It's not going to be easy. In fact, that we'll be dealing with the joint PMF and the PDF, but I do want to introduce it just so you have that kind of connection. So we can find probabilities of events using the joint CDF as well. Okay. Now I'm skipping a lot of algebra and I'll call it a bit of algebra, but it's actually quite a bit. So for example, we could show, and I'll highlight or I'll underscore could, we're not going to, we could show that the probability that A1 is less than X is less than or equal to B1 and Y is, X2, I'll use X1 and X2, sorry. Could use X and Y, and usually I end up using X and Y, but here I have X1 and X2. So X2 is less than some B2. So now, right, this portion, if X1 is between A1 and B1, that looks really similar to what I had up here, right? Besides the inequalities, but the inclusion exclusion doesn't matter, especially on or not especially, it doesn't matter on a continuous scale. So that's why I didn't specify here. But it does matter on a discrete scale. And so here, if I think about, okay, X1 is between A1 and B1, and X2 has to be between some constraint A2 and B2, what I can do is we could show this, and we're not going to, because we're not really going to use it that much. But we could show that this is going to be equal to the joint CDF, and I'm going to drop the subscript X1, X2, but it should be a capital F. And I'll put X1, X2 here just so you can see what should be there, but I'm dropping it. Between B1 and B2 minus the CDF between B1 and A2 minus the CDF of A1 to B2 plus the CDF from A1 to A2. We're not going to do that, but there it is, right? We're not actually going to use this because it turns out that it's a lot harder than what I'm about to show you. Okay. We should have a subscript on all, on all F, right? All CDFs, but we dropped them because so far we only have one CDF, because so far we only have one joint CDF FX1, X2, right? And so it has to be that. Okay. And so we're not going to expand on this, right? Because like I was saying, it's going to be a lot easier to work with the PMF, the probability mass function, or the PDF if we have a continuous function, that probability density distribution, or the function. And so we will not expand on this because it will be a lot easier to work with probability mass and density functions. Just as a little reminder, the PMF is for discrete random variables, and the PDF is for continuous, random variables. We'll start just like we usually do, or we have been in the past. We'll start with the discrete random variable. It is an important reminder. Yeah, I'm glad. And I actually remember the day that I realized this. I'm sure my profs were telling me all the time, but it wasn't until I don't know, one day I saw it and I said, oh, a PMF, that's for a discrete random variable. The PDF, that's for a continuous random variable, but they're the same. Well, it made it a lot easier. So that's why I put it in there just in case. So I'm glad that it helped. So we'll start with the discrete random variable, and then we'll move to continuous random variables, right? And so discrete random variables, we have to use summation, right? Because we're going to find probabilities up to and including some point, and so that's going to involve summations, whereas continuous random variables, then we have to integrate, right? Find the area under the curve, a little bit trickier. Right, we have to draw on our calculus skills, or potentially build out our calculus skills. But this isn't a calculus course, so I'm going to try to show you and kind of give you tools to deal with that. We do need some calculus though. But before that scares you, let's just see what we've got in store, and we'll go from there. So let's talk about two discrete random variables. Okay. Let's just remember what it means to be discrete, right? Because I think that's what we're, the question about all variables being quantized comes from is, well, you know, if we think about a continuous random variable, we usually stop at some decimal place, right? And so then we start to think, well, could it be discrete? Right? Does that make it discrete? And so just as a little kind of helper, a variable is discrete if it has a finite number of outcomes, right? Or it's countable, okay? And so remember, recall that a random variable is discrete if it can take on either a finite set on, I should say either, because it doesn't have to be both. In fact, it can't be both. Either a finite set of values. So an example of that would be 0, 1, 2, 3, right? That if those are the only outcomes, then it's discrete because you have a finite set of values, right? Take on either a finite set of values, or, whoops, hey, what happened here? Or at most, countably many values. And what I mean by that would be 0, 1, 2, 3. Notice how it can go to infinity, right? Should one imply the other? No, because a finite set is always going to be part of a countable set. But in theory, we could count to infinity, right? You can keep going and going and going and going. And so when we say countably many values, it does go to infinity. And so, so that's kind of weird to think about when we say countable, but they're going to be separate, right? Because if you have a finite set of values, then this list ends. Even if it goes to 10,000, right, it would still end at some point. And so then you'd have a finite set, whereas countable values would go from 0 to infinity at most. I don't know if I answered the should one imply the other. Okay, good. Good. Okay, so in either situation, right, we don't consider the values in between here, and that's what makes it discrete. Right? And of course, this could be 0.1, 0.2, 0.3, 0.4, but if we're only moving up in increments of 0.1, right, it would still be discrete, right? So they don't have to be whole numbers, although typically they are. And that's where it gets a little bit crazy with z-scores, for example, rounded to 2 decimal places, but they exist on the entire scale, right? And that's what makes them continuous. So just because we don't want to write them all out doesn't mean they don't exist. Okay, so that was a reminder that I wanted to kind of throw in there. But if both random variables are discrete, right, then we can describe a joint PMF by how they change together. Right? And so if both random variables are discrete, we can describe sorry, because I wanted to cut some stuff that I had in here. So I'm just trying to make sure it makes sense before I cut it. So I had, if both random variables are discrete, we can describe the joint CDF will once again be constant. No. We can describe, I'll just go with what I have. Situation, even though it's not very elegant. if both random variables are discrete, we can describe the situation using a joint PMF, which is going to look like a lowercase p x1, x2 of x1, x2, right? So now we have two inputs, x1 and x2, which is the probability of, and maybe I'll use a big square bracket here, that x1 is equal to x1. So capital X1 is equal to lowercase x1. And capital X2 is equal to lowercase x2. Because the PMF gives us the probability at each point, right? But now X1 can take on some set of values, as well as X2 can take on some set of values, right? So X1 can take on a set of values, and X2 can take on a different set of values. Okay. So we allow them to change, right? X1 might be 0 and X2 might be 3, right? That's a different combination than 0, 1, 0, 2, 0, 3. Well, not 0, 3, that's the first one that we started with, but right, so they can vary together. And so there's going to be some joint probability function. And so that's why we call it the joint probability mass function. This is the joint probability mass function, right? The probability of some combination X1, X2. So if we want to think about a quick example, we can think about flipping a coin. We love coin examples just because they're nice and easy to wrap our heads around at this point. And we can do a lot with flipping a coin. And so, for example, if we flip a fair coin just means the probability of one side is 0.5 and the other side is also 0.5. If we flip a fair coin 3 times, we can let X be the number of heads, and we can let Y be something weird. We can let Y be the number of tails before the first head. There's so many different scenarios, even with just flipping a coin 3 times, there's so many different scenarios that we could come up with that we might be interested in, right? And so in this case, if we let X be the number of heads, and I'm going to use Y in this case because X1, X2 makes kind of a mess. So X and Y instead, but they take the same place. Y is the number of tails before the first head. So what that means is if we toss tail, 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 we'll call that 3. Okay. So that's just to clarify a weird situation where the number of tails before the first head in 3 coin flips, if we do all tails, we're going to call it 3, even though we didn't see a head, right? But that's just the definition. So Okay. The number of heads and the number of tails before the first head, they're going to happen, right? They're coming from the same outcome, right? So both of these random variables, although they're looking at different things, they're going to come from the same outcome. So what we'll see here is that one outcome will generate two random variables. Will generate two random variables, right? So what we can do is we can work out all the probabilities. So we can work out the probabilities by first listing all the possible outcomes. By first listing all the possible outcomes. Could it be solved using a tree diagram? That is a good question. With 3 coin flips, I'm trying to see if we can do it, because we're going to want to have, so eventually we're going to work up towards the CDF, the cumulative distribution function. So then that would require a little bit of work, but I'm not seeing it clearly, but I'll think about it some more. Maybe you can solve it with a tree diagram because it's only 3 coin flips. I don't see it right in front of me, but something to think about. So I'll think about it. But if we list all the possible outcomes, then we can have our outcome, which we'll call C, lowercase c, doesn't matter what you call it. O is kind of weird. We try not to use O, the outcome, because it looks like a 0. So you don't want to throw yourself off and start multiplying by 0 when it should really be C or some constant, right? So you don't want to throw yourself off. So we'll use C for the outcome. So all our possible combinations, we could have head, 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 tail, head, tail, head, right? Just changing one thing as we move through here. Head, tail, 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 head, head, tail, head, tail, 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 head, tail, tail, tail. So now, if I want to think about the probability of each outcome, well, with 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes, the probability of each outcome is the same. And so 1 in 8 for all of these. What if I think about X? Remembering that X was the number of heads. So I can record X for each of these outcomes, right? I had 3 heads, and here I have 2 heads. Here I have 2 heads, 1 head, 2 head, 1 head, 1 head, no head. Okay. What about Y? We said Y is going to be the number of tails before the first head. right? And so the first head happened on the first coin flip here. So that would be 0, right? The number of tails before the first head. Sometimes it's hard to kind of formulate these, but once you get the hang of it, it's not so bad, right? So 0, all the ones that started with a head, that's going to be just 0, right, for y. I'll start there. And then now I'm considering tail, head, head. So the number of tails before I got a head was 1, right? So 1, same thing with the next one. It doesn't matter what happens after that first head, right? And so here, tail, head. So 1 tail before I got a head. And then here, tail, tail, head. So now I have 2 tails before I hit a head. And so 2. And finally, tail, 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 we decided we would denote by 3. Yeah. So what we can do is we can look at all of these XY combinations to generate our PMF, our probability mass function, for these combinations of X and Y. Right, and so here we consider these combinations of X and Y to generate the PMF. Okay, so the probability of 3 then 0, right? X is 3, Y is 0 is 1 in 8. The probability that X is 2 and Y is 0 is 1 in 8. But what we see here is that these two situations, this is the same, right? 2, 0, 2, 0, right? So it didn't matter how we generated them. So what we're going to have is a probability that X is 2 and Y is 0 is actually going to be 1 over 8 plus 1 over 8, which is 2 over 8. So these are the same. Okay. So what I'm going to do to generate the PMF, right? We can now construct, even though I sort of said something similar up above, but we can now construct the PMF by considering all combinations, by considering all the combinations. So what we have is I have some lowercase p x y of x y. Now, I will make a note here because I always find that, or found it really confusing, but all these subscripts are denoting which random variable it's using. So those are going to be capitals, whereas these variables inside the brackets are always going to be lowercase because they're referring to the outcome. So just as a quick note, these are lowercase, right, because they're outcomes. And these are uppercase because they're random variables. Okay. Just to kind of help sort of make sense of things. So what we get is, well, we can start with our combination, and I had left room here for a big piecewise function, but it's okay. If X is 3 and Y is 0, Right, try to keep it, can't seem to have it on the same page, but so my first combination is 3, 0, right? The probability of that was 1/8. This situation that we highlighted here, that's the only situation where I have the same scenario, right? The same value of X and the same value of Y. And so that's the only time that I need to combine these probabilities. You can scan the situations, right? 1, 0, 2, 1, 1, 1, 1, 2, 0, 3. Those are all different, right? And so now we can construct this and say the probability is 1 in 8 for that. The only one where it's not 1 in 8 was when X is 2 and Y was 0. All the other situations are going to be 1 in 8. So X is 1, Y is 0. X is 2, Y is 1. X is 1, Y is 1. X is 1, Y is 2. X is 0, Y is 3. And lumping all the other cases in with each other. Otherwise, the probability is 0 because they're not going to happen. So this is 1 in 8, 1 in 8, 1 in 8. So sometimes we summarize this because this is a really big, just kind of piecewise function, right? And so sometimes it's easier to summarize this as a table. How would we construct our table, right? And so sometimes it is easier to construct the PMF as a table. So what we have the probability of X, Y, oops, it's a capital Y, X, Y. If Y, it can be 0, 1, 2, or 3. Same thing with X. X can be 0, 1, 2, or 3. We can join these up with the probabilities that join up. It's going to be the same information that we had here. So I'm just going to go through and list them out, right? But I'm just showing you that there are two ways to kind of produce this information or summarize this information. 0, 0, 0, 1 and 8. I'm just going to deal with the 2 and 8 situation right away. That's when X is 2 and Y is 0. 2/8. And then the rest are actually going to be on a diagonal here, 1 and 8. 1 and 8, 1 and 8, 1 and 8. The rest of these will be zeros. There. So from here, we could build up the joint CDF. Okay, so we need to incrementally increase X, right? Holding Y steady. And then we need to let Y change, right? So we need to increment through X, let X change over all the values. In this case, it's only 0, 1, 2, and 3. And then we let Y change over all the values. And then we need to consider all the different combinations of 0, 1, 2, 3. That gets pretty big, right? And so what I was thinking I would do is we're not going to write them out here because it's 14 lines. I counted in case you're like me and you want to leave space, because I'll put it in the notes so you can fill it in later if you want to. But I'll leave some space here to fill it in, and it takes 14 lines. Okay, and so here I'm just going to say from here, we could, been saying that a lot lately, we could do this, we could work out the joint CDF, right? The cumulative distribution function. We use the same acronym for discrete as well as continuous random variables, right? And so the CDF works for both. How we find them are different, but we will find it's a lot more convenient to work with joint, with the joint PMF, sorry, with the joint PMF than the CDF. One, two, three, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So here, leaving 14 lines to show the CDF in the notes later. Of course, I'll erase this here. So if you want to leave space in your notes, you can. If not, it'll be in my notes that I post. Okay. But instead, we'll use the joint PMF to calculate probabilities. And I just want to do maybe 1 or 2 examples here to show you. So instead, we will use the joint PMF to calculate probabilities like the probability that x plus y equals 2, referring to the previous question, from the coin example, coin toss example, right? What's the probability that x, which was the number of heads, and plus, or was it tails? I've forgotten already. So the number of heads, well, let it catch up. Sorry, x is the number of heads and y is the number of tails before the first head. So what we want to consider is if we have the list of possible outcomes here, we can easily look to find things like, and maybe what I'll do is I'll copy this so that I can show you. You can do it on this one if you want, if you can make it make sense, right? But here, what we have, oops. Is we can find x plus y. Well, if I go through and I add x and y here, right, then I can find all the values where it's 2, right? So here it's 3, here it's 2, here it's 2, here it's 1, here it's 3, here it's 2, here it's 3, and here it's 3. So if I want to know the probability that x plus y equals 2, well, I can look at all the situations where that happens, right? It happens here, it happens here, and it happens here. there are other ways that you can get to this, but I just find that this is the easiest way to look at it because we have this table, right? And so if I want the probability of this happening, we already combined in the PMF, right? We could use the PMF because we know the probability of 2, 0 is 2/8, right? And so this is going to be the PXY of 2, 0 plus PXY of 1, 1, which is 2, 0. The probability of that is 2/8 plus 1, 1 has a probability of 1/8, making a total probability of 3/8. What if we wanted to do something a little bit more advanced? Maybe don't want to, but what if we had to? So for example, or another example, the probability of X less than or equal to 2 but greater than 0, and Y is less than or equal to 1. Again, you can look at all the different outcomes to figure out, okay, when is this going to happen, right? And so when is X between 0 and 2, right? So it has to be greater than 0, not equal to 0, but it can be equal to 2. So 1 or 2. So that happens here, 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 right? I guess that's not, here, here, here is not very helpful if you can't see the screen, but anyways, I'm assuming you can. So the different scenarios that we could look at, right, is, oh, and then Y has to be less than or equal to 1, which excludes these last two options, right? And so what we can do is we can list these different scenarios. Because there's quite a few scenarios, I'm going to leave myself lots of room and put the equal sign down below instead. PXY of 1, 0 satisfies it, plus PXY 1, 1 satisfies it, plus PXY 2, 0. Notice how we could drop the subscript XY if we want to. Right, I just want you to get used to seeing it so it's not so scary when you see it. Right, you can kind of ignore it even. Plus PXY 2, 1. Right, so if we had, I'm going to copy this here, copy. If we wanted to see here, if X can be less than or equal to 2 but greater than 0, those values would be these ones here, right? And if Y has to be greater than or equal to 1, oh, sorry, less than or equal to 1. That's these guys. But then these two we decided were the same. So the different combinations are 2, 0, 1, 0, 2, 1, 1, 1, right? And so that's where these 1, 0, 1, 1, 2, 0, 2, 1 came from, right? Because these, there's no overlap here. So that situation is excluded because Y has to be less than or equal to 1, Okay, so that's where these scenarios came from, but we have these probabilities because we developed the PMF, right? And so this is going to be 1 in 8 plus 1 in 8 plus 2 in 8 plus 1 in 8, trying to keep it kind of off the table there, which if we add this up becomes 5 and 8. Oh, I'm out of time. I had just one last thing I wanted to write out. If you have to go, I understand, but I'm just going to write this last thing out. So in general, what we're going to have is the probability that X and Y are in some A, going back to where we started, right? Which felt weird at the time. So if the combination X, Y are in some space A, then that's going to be the sum where X, Y is in A. So all the situations where X and Y are in some A of the PXY of XY. Done. Okay, so in general, what we do is we just add up those PMFs that apply. Okay, I'll end it there. If you have any questions, let me know. Otherwise, I'll see you guys on Thursday. I can never keep my days straight. I'll stop this recording now.